Hey guys, how's it going? Today I want to talk about the chlorination and bromination of propane and their selectivities for the secondary carbon position. And we're going to explain it using the Hammond Postulate. But first, I just want to go over the reaction. So both of them are going by a free radical mechanism. And when you actually do this reaction in the lab, you get different relative amounts of your products. So for the chlorination of propane, your two monochlorinated products are 1 chloropropane, and 2 chloropropane. So when you actually do this reaction, you get about 40% of your 1 chloropropane and 60% of your 2 chloropropane. Likewise, you can do a free radical bromination, and the relative amounts you get are actually 3% for your 1 bromopropane and 97% for your 2 bromopropane. So both of these have a sort of tendency to react onto the secondary carbon position, this middle carbon here, but bromine we say is more selective, as in it prefers the secondary position more than chlorine does. So it's a little pickier about where it goes, and that's why you get 97% of that compared to 60. First, I want to talk about why they prefer the secondary position. And to do that, we have to look at the radical stabilities. If you remember in the mechanism, you need to have a radical that's going to abstract the halogen from either it's going to abstract a chlorine from Cl2 or a bromine from the Br2 in the same sort of like this. So to do that, you have to first produce this radical. I'm going to draw out a couple different kinds. The first is a tertiary radical. So each of these lines means it's being connected to a carbon. And then, so there's 3, so it's tertiary. This one is secondary, so 2 carbons and then 1 hydrogen. And this last one is primary, attached to 1 carbon, and it has 2 hydrogens here. They're all radicals. And what I want you to notice is that each of these are just 1 electron shy from having a full octet. So they need just one more electron for them to be happy. So if you don't know already, it's worth memorizing that alkyl groups, or carbons, are electron donating. So they give electron density. The one with more carbons is going to donate more electron density. So the tertiary radical is more stable than the secondary and primary, and the secondary is more stable than the primary because they're getting more electron density donated in, so they're getting closer, you could almost say, to having a full octet. So since these reactions require the radical intermediate, the secondary is going to form much more often than the primary, so our secondary position is going to react much more than our primary positions. But that doesn't explain why the chlorination ratio is so different than the bromination. To do that, we have to actually look at the reaction. So I'm going to erase this real quick, and I'm going to put up a reaction diagram. So that's going to help explain why we get the product ratios we do. So on our y-axis, right here, I'm going to have energy. So this is just relative amounts of energy. We're going to do this qualitatively. We're not going to use any numbers. And then down here is just where we are in our reaction. It's not necessarily time, it's just keeping track as you flow through your products. Our starting point is going to have this much energy, and I'm going to say we have the propane and then our halogen radical. So, and I'm going to use this to represent both the chlorination and bromination. So first, let's look at the chlorination. What's going to happen is this radical is going to abstract a hydrogen from the secondary carbon, pull it off, and then leave that carbon as a radical. So that's going to require you to put in some energy, but then overall you're going to get a release of energy, like this. So your reaction is going to be overall exothermic. And you're going to end up with this propane radical, and then HCl. Remember, we're doing the chlorination right now. So this point up here is called your transition state. It's sort of like an intermediate, but it doesn't actually exist in real life because you can't actually isolate it. And the reason is because when you think about what's going on here, you have your carbon, and then the hydrogen is partially being pulled off by our chlorine radical, but it's partially still bonded to the carbon at this point. So I'm going to just represent that by putting dotted lines connecting them. So it's part bonded to chlorine, part bonded to carbon. We know that actually can't happen in real life. It's a theoretical position, but it's going to be useful to think about it in this way. Now for our other reaction, the bromination of propane, it's going to be very similar. It's going to require a little bit more energy input, but then at the end, you're actually going to end up putting all this energy in and not getting any energy out. So it's overall endothermic. Our products are still the radical, and this time HBr. And this likewise has a transition state, this point of highest energy, and it's going to look just like this except a bromine up here. So what we need to think about now is Hammond's postulate, and that's going to help us explain the different selectivities of for the bromination and the chlorination in a free radical mechanism. So the Hammond postulate states basically that your transition state is more structurally related to the species that is closer in energy to. So let's look at the transition state for the chlorination. If you look at what it's closer in energy to in comparison of the reactants and the products, you can see that the smaller energy difference is between the transition state and the reactants. Therefore, we say that the transition state more closely resembles our reactants. So I'm going to represent that over here. So our reactants are the chlorine radical and a bonded carbon to hydrogen. So I'm going to represent the radical with dots and the bond with dashes. So you can kind of see here, there's still radical character, there's still part bonds between these, but you have more bonding character between the carbon and the hydrogen, and more radical character between the hydrogen and the chlorine. Now let's look at the bromination. So in this case, if I draw the differences in energy between the reactants and the products, we're going to see that there's a much smaller energy difference for the transition state between the products. So we're going to say that the transition state more closely resembles our products. Therefore, I'm going to draw over here. It's going to be similar. I'm going to make some room. So I have our carbon. It's bound. The hydrogen down here. The hydrogen up here is partway between the carbon and the bromine. Except now, since it resembles our products, there's radical character on this carbon, bonding character between the hydrogen and the bromine. So it's going to look like this. Now we have to think back to what I originally said. If you remember, the secondary carbon is going to stabilize a radical better than a primary carbon. So we already got that out of the way. In these two being compared, there's much more radical character on the carbon during the bromination reaction. That's going to make the bromination reaction more picky for the secondary carbon, because radical stability is going to come much more into play. Whereas for the chlorination, radical stability still comes into play, obviously, because the secondary carbon is more reactive, but it's less as a factor as it is for the bromination. So that's why the bromination is so much more selective than the chlorination. So Hammond's postulate can be applied to a bunch of other situations, and it's pretty useful to help us kind of theoretically imagine what a transition state looks like. And it's especially useful for explaining this concept. So hopefully you have an understanding of how it works now. If you have any questions, you can email me or comment on the video. All right.